Well, thank you very much. Thank you for the organizers for the invitation here. I enjoy a lot this meeting. So my talk will be a bit similar to the previous one, but there is different analysis. Let me see. Yeah, so the extra dimensions start with some motivation. It's an important ingredient of theories of quantum gravity, such as string theory. And we know already from the past that if they are large compared to the string scale, then gravity becomes strong at energies lower than the Planck scale. And typically, this is the higher dimensional, which I call M star, the higher dimensional Planck scale, in which case our universe would be localized on some free brane. This framework was recently motivated, had additional motivation and different framework by the proposal of dark dimension from the dark energy, which is a consequence of the Swampland distance conjecture, which when you put together with observations, one finds that there should have, as a consequence, there should have one or two extra dimensions of micron size. My talk, I will mainly talk for one extra dimension, but it is also a possibility.
Some fine-tuning for the two.
Yeah.
Two dimensions, extra two dimension, I think the bound that the Oxford group gets is less than 0.2 micron, would be the length. So 10 micron is a natural scale, so you have to factor of 50 there, and then BBN is also fine-tuned.
Yeah, it's very constrained. It's very constrained. Very constrained. I agree. So this the higher dimension of Planck scale, 5 dimension. In case of 1 dimension, it's 10 to the 9 GeV. We use the reduced Planck mass. I think that's the difference between 10 and 9, and or 10 TeV in the case of 2 dimensions. And that's the validity of the Newton's law, which is 30 microns. So just to go fast on the Swampland distance conjecture, which so the point is that if there are if some physical parameters which are small, we had before, but are dynamical in the sense they are determined by vacuum expectation values of moduli fields, then you're forced to take large distances in the field space, in which case there is a tower of exponential light states, which typically is Kaluza-Klein tower. It could be also, of course, string tower, but then it's the string coupling instead of the extra dimension, where the tower, the scale of the tower is the compactification scale, and the distance is the logarithm of the radius or the size. So applied to the dark energy and motivated by ADS vacuum, which as we had before, there the distance is the logarithm of the cosmological constant, and assuming that this is true also for de Sitter space, then one finds that the mass of the tower should be the power of the cosmological constant. Then you put together the experimental bounds, and you find that the tower should be 1/4. And the size of the extra dimension is the micron size. So what I had in mind, I think the simplest picture of this type is either an orbifold that I mentioned before, or starting from M theory, which for which 1 dimension is singled out, the 11th dimension of the M theory, in which in 10 dimensions you have the 2 E8s are on the boundaries, and 10-dimensional boundaries. In that case, the size of the extra dimension is the 11th dimension of the M theory. The compactification is an interval, as we had before. So I will discuss physics implications. Just go first flash rapidly through the rest. So we heard already about new dark matter candidates. We heard the possibility that the dark matter is composed of calcium gravitons with decreasing mass due to internal decays. And this could provide a realization of the dynamical dark matter proposal, where the dark matter is peaked its mass around MeV at high temperatures, and it becomes lower today. Another possibility is that dark matter is composed from 5-dimensional primordial black holes. And then the observation was that if you compare a high-dimensional black hole with a 4-dimensional one, which has the same mass, then the high-dimensional black holes live longer, and therefore one can get rid of partly of the evaporation bounds, which are the lower bounds, which allow a full dark matter interpretation as primordial black holes for an extended region, which is from 10 to the 15, from 10 to the 15 to 21 grams. So this in grams, these solar masses, and this is a fraction of black holes to the dark matter. So the 100% dark matter, you should just look at the upper line. And of course, yeah, 6 dimensions, it's even higher, the larger the range. There was also applications cosmology. One possibility, for instance, that was there was questions today and yesterday about what happens before the initial condition, which start with the brain, and then you produce calcium excitations, is to have a 5-dimensional inflation in which compact dimensions and the non-compact space, our universe, expands uniformly in the same way, starting with some initial condition with a size which of the order of the fundamental length, and then blow it up to the size which is needed in order to explain the weakness of gravity, the black mass. So in that case, inflation should last a finite epoch, and one can relate two hierarchies, the size of the observable universe to the weakness of gravity. We also heard today about possibility to explain dynamical dark energy by a variation today. What I will discuss is neutrino masses, which it was known from the past that when the gravity scale is low, then there is a question how to explain the small neutrino masses, since for the seesaw mechanism, one needs a high scale, perhaps not too high. In the case of 10 to the 10 GeV, is not too higher than this. And a natural possibility is that to introduce the right-hand neutrino in the bulk, in which case the smallness of the neutrino masses is due to the wave function suppression of the right-hand neutrino. And this was a case that was studied in the past and has been studied also in the context of oscillation data. That was one of the in which one can find the bound on the radius. And also it was pointed out that this bound, I mean, most of the previous analysis was based on the assumption that the right neutrino with the bulk state has zero masses. In the case of non-vanishing bulk masses, it was already pointed out that these bounds can be relaxed, and I will make it transparent in the following the talk. So the main some of the main consequences of this framework is first that the Kaluza-Klein excitations are towers of sterile neutrinos, since they don't have standard model interactions. The neutrino masses are most likely of Dirac type. And there's a possibility to have bulk masses for the neutrino. So I will, before going into the analysis, I will just motivate a bit these three consequences. So the first one is that is a basic mechanism which goes back to 98. So you have a right-hand neutrino, which depends on a bulk coordinate, let's say one extra dimension. Then one can have a neutrino right interaction to the brain. We heard that in a compactification of on an interval, the parity, which you use to divide S1 over Z2 to describe the interval, corresponds to chirality, to gamma 5 transformation, and therefore what happens is that the bulk state, which is a 5-dimensional spinor, has a zero mode which is composed, let's say, of a left-handed and right-handed. One part of the zero mode couples to the brain with a Higgs and the lepton doublet. And the other part is projected away from the projection. So if one introduces a coupling of this sort, then this coupling is dimensionful, so it has to extract the dimensions by the high-dimensional Planck scale. And then I define a Y, which is a dimensionless parameter. I have to take out this, deny, always. I don't know. I don't know what to do, allow or deny. Now, once one turn on the Higgs expectation value, it doesn't like it. There is a mass term which is generated. And if I express the right neutrino at the origin of the extra dimension, then this is represented by a sum over all the Kaluza-Klein modes with a normalization, which is the volume factor of the extra dimension. And therefore, this volume can be re-expressed as the ratio of the high-dimensional Planck scale over the 4-dimensional Planck scale. So what multiplies this dimensionless Yukawa coupling is the vacuum extension of the vacuum of the Higgs field times m star over m Planck. Now, in 2 dimensions, which was considered in the past, this scale, this mass scale, is milli-electron volt, and therefore this implies that mixing with the Kaluza-Klein states is not important, as essentially this determines the value of the zero mode, so the neutrino mass, which is in the right ballpark. In the case of 1 dimension, this ratio is large, is about 100 electron volt. And this is what I think Miguel also was mentioned at the beginning. I will see in the moment that this is not a problem problem to get the right masses once you take into account the mixing of between the active neutrino and all these Kaluza-Klein modes. I don't know how to take out this thing. No, sorry. So now let me talk about this Dirac neutrino masses. The nature of Dirac neutrino masses is, gets also additional support from a different from another Swampland constraint, which says that the non-supersymmetric ADS vacua are unstable. And there was this seems to be in conflict with an observation that was done in this analysis in the past, that the standard model with Majorana neutrinos has a vacuum in lower dimensions, which is added de Sitter in 3 or in 2 dimensions, in which the radion is stabilized coming from the 4-dimensional cosmological constant, is stabilized with a Casimir energy.
This analysis was done in the context of no dark dimension, right?
Yes.
So now there's a light tower of...
Yeah, I will mention. So just to tell you the mechanism, one starts with a 4-dimensional, let's say, cosmological constant. Once we go to 3 dimensions, then one obtain the potential, which is 1/r² times the cosmological constant. And then there is a Casimir energy, which behaves in this way like 1/r6 once one renormalized the kinetic term in the proper units. And this Casimir energy, one contributes the number of bosons and fermions, which are light. By light mean lighter than the compactification scale, than 1/r. So for bosons, we have the graviton and the photon that has 4 degrees of freedom. While for so this gives a maximum, and it goes down. So that's the potential as a function of the radius. But then there are the neutrinos, which have masses somewhere here. And if you consider 6 fermion states, which correspond to 3 Majorana neutrinos, then one finds an added de Sitter vacuum, which was pointed out by that reference. Now, it was realized that if instead of taking Majorana neutrinos, you take Dirac neutrinos, then effectively you double the degrees of freedom. Then this curve goes up. Of course, it depends at what value you have the masses of the Dirac neutrinos. So the condition that there is no added de Sitter vacuum is that the lightest Dirac neutrinos should have a mass less than 7-8 milli-electron volt. So this argument supports Dirac neutrinos. And then I discussed the case of bulk masses. So this is, I mean, one can in principle take this mechanism that was analyzed in the standard model and then upgrade it to 4 dimensions, starting from 5-dimensional theory. So one can, again, starting from a 5-dimensional cosmological constant, obtains a potential that one could try to stabilize the radius by the Casimir energy. In that case, you have the 5-dimensional graviton, which has 5 bosonic degrees of freedom, which could create a maximum. And then one needs, in order to find the minimum, one needs to inject fermions. And if one considers that there are 3 right-hand neutrinos, then one obtains the right fermionic degrees of freedom to curve up and find a minimum, which now this is in 4 dimensions. And in this is a way to stabilize the extra dimension. Of course, one needs initial value for the 5-dimensional cosmological constant in that case. So now let me go to.
Sorry, let me just.
Yes.
I was thinking maybe you have answered.
Yes.
Suppose you just go to 4D mass spectrum.
Yes.
And add to it just the KK tau.
Yes.
And redo the analysis.
It's similar to this.
So you still get an ADS vacuum?
No, it's similar to this. I mean, you need right-handed neutrinos.
Oh, I see.
I mean, you have to cancel the tower of the gravitons.
You're saying 3 right-handed neutrinos
cancel, yeah,
gravitons?
Yes, cancel.
Exactly.
I mean, cancel as you need in order to produce a vacuum, which is.
It depends on the detail, exact mass. Exactly. A slight difference will change.
Of course, yeah, the mass has to be less than the.
Not just the scale.
Yeah. The mass of the neutrino should be less than the micron.
This just to make sure the scenario that Miguel talked about, where the mass of the neutrino starts at 100 keV, or 1 to 10 keV.
No, this is too big.
Sorry?
This is too big.
So therefore, there would be no ADS vacuum. No. So it's consistent with not having it.
No, this is too big to create a minimum.
Yeah, so there's no ADS minimum, you're saying.
Well, there is a maximum though from the graviton.
I know, but I'm just saying there's no contradiction with the stable ADS then.
No, but but then the potential has no minimum if you don't introduce.
If you try to compactify it to 3D, there's no compact.
No, to 4 dimensions. This was to study. Yeah, I was talking about to stabilize the dark dimension in 4 dimensions.
Don't want to stabilize your good.
Yeah,
like what we needed for a talk that we heard yesterday from George's. So it depends on what we want to do.
Right. That was
to
stimulate.
Different. My question is stimulate. I was questioning about going to 3D.
3D. This.
So they were. I mean, in the paper, the Neiman company were trying to find
exactly
that if you study standard model spectrum, whether or not you can get ADS, and it depends very much on detail of neutrino masses and so forth.
Yes.
And then you're talking about this band. I'm saying, has that been updated using in the context of dark dimension? That's my question.
This is the same bound essentially. That there could be a Dirac neutrino with a light mass less than 5. But this is 0 mode. No, this does not change. It can be improved if you have a light gravitino, then can replace the light gravitino by the.
Well, there are light gravitinos in the KK mode. That's exactly what I'm saying.
But in the milli-electron volt range. In the milli-electron volt range.
They are in that range, the KK modes, right?
Yeah.
I think they're above.
What?
I think they're above.
Depends on what you take exactly, right? You're talking about KK mode is in the.
I mean, that's the condition. It was similar. I think the bound on the light gravitino, it was similar to this.
But you have the power.
The point is that with a micron scale, all the thing gets up, the electron volt, and it's out of the range that makes that term.
Sorry, I'm not sure. There's an infinite tower of these guys.
Yeah, but they start
at around 10 milli-electron volt or something. Depends on exactly what size you take.
Okay, well, yeah.
So it's definitely of the same order. Now, so one of them, 2 of them, how the polarization.
If you lower the tower, this.
So nobody has analyzed that. That's.
Yeah, we have
analyzed it.
Ignatios and Jules.
We have found the conditions.
Yeah, all the values.
You have the 3D conditions?
Yeah, I think Jules did that thing.
Yeah.
Yeah, can discuss.
I mean, it's that paper over there.
So let me go now back to the analysis of this analysis first. Okay. So we have the coupling to the Higgs and the lepton of the right-hand neutrino, and in addition we have the Kaluza-Klein state. Then the extra dimension is compactified on an interval, and then the right-handed part of the 5-dimensional neutrino couples to the brane, so it's expanded into cosines, while the left-handed part doesn't couple to the brane, is expanded into sines with functions. And then one has to diagonalize this infinite by infinite mass matrix that was shown by Miguel. Essentially, this is the eigenvalues are given by the roots of this equation. So mu bar is mu, which was this coupling, the Yukawa coupling essentially mass, times the radius, so to make it dimensionless. And then there are two regions. The region where mu bar is small, so the mass that you obtain from the Yukawa coupling is small. In that case, the roots of this equation are just the 1 over r, but the zero mode acquires a mass of order mu. And then there is the other, this was the case for 2 extra dimensions that I mentioned before, because mu is naturally small. While in the opposite case, where mu bar is large, then what happens is that this equation has now solutions when the cosine, mu bar is large, so it has solution when cosine goes to 0, which means that the eigenvalues go to half integers. So even if the Yukawa coupling here is large with y of order 1, still the Kaluza-Klein states, including the mass of the lowest mass of the active neutrino, is proportional to the compactification scale. So this relation lambda to the 1/4 is valid. However, in that case, the active neutrino, the active neutrino is composed of Kaluza-Klein states, which peak. We start from mu bar, so they don't start from 0, but they start essentially from a higher Kaluza-Klein state, which should be taken into account, of course, when we make analysis of the oscillation.
Sorry, I didn't get that. What say? Why does it start from n? What about lower n?
This is the eigenvector, which corresponds to the lowest eigenvalue. Okay, so you have to diagonalize infinite by infinite. So you find the eigenvectors, the eigenvalues, and the eigenvectors. The eigenvectors are picked, essentially from the coefficients are non-vanishing for the states which are higher excitations.
There was a debate we had with Miguel with the collaborators, which were talking about something which I don't know if this relates to what you're saying, but they were saying there's a periodic effect as you increase the things, the nth one becomes massless.
No, that's a different. I will talk about this. This was with this is with a mass. This analysis without bulk mass.
So you're not putting a bulk 5D mass, then you will put a 5D mass, and then it's going to be zero.
I will discuss this in a moment. Yeah, but without bulk mass, that's the
mu bar for you is what again?
Mu bar is the coefficient of the Yukawa coupling. So mu is essentially the Yukawa coupling. Mu bar is times r. Well, yeah, I think I defined before. So it's mu times r. Mu in terms of the compactification scale.
So if mu bar, so can we go back to your next slide? So if mu bar is large,
yes,
very large, like you're
yes,
there,
all
these small n's are going to be very massive.
No, the eigenvalues are half integer.
I know.
And the eigenvectors have these linear combinations.
Oh, so
they are dominated.
So the light ones are still small n.
Yeah, then of course, the n equals 0. I mean, you start with 1/2.
So you're just talking about eigenvectors.
Yeah, these are the eigenvectors. So since mu bar is large, the eigenvectors start from from higher excitations.
Eigenvectors of light mode start from higher n.
Yeah.
But their mass corresponds to small n.
Yes. I mean, the coefficients are small. This is an approximate formula. No? It's, of course, there are corrections, but that's in the large mu bar limit. That's the this is the eigenvector. So now I'll discuss the case of non-vanishing bulk mass. So if you have, I call it C, the bulk by, because that's how the literature was written the first time. So C is a bulk mass, and the bulk mass shifts the Kaluza-Klein states by the masses by this way, by C square. But then you have to diagonalize the mass matrix. And the eigenvalue equation now has, there are two types. There is either with a cotangent like here, which gives more, almost all the eigenvectors, all the eigenvalues except possible the lowest one. And the lowest one satisfies, depending on, satisfies the cot hyperbolic equation. So X are the eigenvalues. So for the eigenvalues which are bigger than the bulk mass, the first equation, the cotangent equation, is valid. While for the small eigenvalues is the second equation. But the second equation has at most one eigenvalue. So just to give you graphically what it means. So the blue curves are the that part, the cotangent part. Sorry. Is this part of the equation? That's the cotangent. And the black curve corresponds to this part, to the polynomial part. So the intersections correspond to the eigenvalues. And the red curve corresponds to the cotangent, cotangent hyperbolic equation. So this can have a solution only for the first eigenvalue or not. For instance, in this case, the red curve has no solution. In this case, has one solution. So it depends on the parameter space. The lowest eigenvalue satisfies the cotangent hyperbolic equation. Now the solutions for the higher modes is just a deformation of this eigenvalue equation by an extra quantity which depends on this parameter. So it just moves this formula. But what is more interesting is to look at the lowest eigenvalue. So if the lowest eigenvalue satisfies the second equation, the cotangent hyperbolic equation, then you obtain this formula for the lowest eigenvalue. So I write it here to see it. So C bar is 5-dimensional mass times the radius. So in units of the co-actification scale. And it can have two signs, positive sign or negative sign, because in 5 dimensions, the sign of the mass is physical. So for positive values, one can have an exponential suppression for large C bar of the zero eigenvalue. So if this was presumably what you were talking before. While for C bar negative, you have just an extra power suppression. And again, this is the eigenvector, which is picked at the state, which is a higher Kaluza-Klein state, when this Kaluza-Klein state is of order of C bar of the bulk mass. And around this state, of course, you have an accumulation of Kaluza-Klein states. So this is the theoretical, let's say, results that can be.
So the outcome here is that you have a 5 degree with a mass.
Yes.
5 different
yes.
So mass C.
Yes.
And then what you're saying is that the mass of the lightest eigenmode when I compact in a circle or interval can be much lighter than it.
Yes, right. Huh? Yeah, that's the formula.
Mass of, sorry, I don't understand. How to put that up?
The lowest eigenvalue for large bulk mass goes to zero, either exponentially or as a power.
This is on a circle.
This on an interval.
Is it
With a
because of
bounded-
interval?
Yeah, it's an interval that you have to impose Dirichlet conditions for the right-handed neutrino of the
But if I take the
five-dimensional.
infinite interval limit, let's say, the radius goes to infinity.
These were finite radius. So it depends.
I know, but if I'm just a bit confused. The 2-point Green's functions of a neutrino exponentially dies off at large distances if the mass is big. So
C bar is the bulk mass times the radius. So if you take the radius to infinity, you have to tell me what you do with C bar. You keep it with a five-dimensional mass. Do you keep it fixed?
fix a 5-dimensional mass.
Then C bar goes to zero in that case.
5-dimensional mass is fixed, I'm asking.
If you fix a high-dimensional mass,
5-dimensional
the five-dimensional
Then the
mass,
Green's function-
then the C bar that I define here
goes to infinity.
goes to zero. Goes to infinity. I'm sorry.
Goes to infinity.
Right. For R goes to
Then there is
for
no
R goes to
first
infinity. Yes, it goes to infinity. Right. Yeah.
So in that case, there's no, then what happens then? In that case, the lightest mass is what?
Well, in that case, it goes to zero.
Eigenvalue goes to zero?
Yes. Yes.
At an infinite interval with a neutrino, I mean, Einstein tells us that the Green's functions of the neutrino and the bulk is suppressed.
I mean, yeah, that's what you find.
It
You.
cannot be. That's there's something.
I mean,
This is the same effect that we were finding.
yeah,
in the-
we had an issue with this with the.
I mean, you just put the mass new left, new right at Z. Okay. And for this state, you put Dirichlet conditions, so nu R at Z equal 0 and pi R, let's say.
If you had put it on
Equal
a
to
circle, would
zero.
it have changed anything?
Sorry?
Suppose I said you do it on a circle.
Of course, yeah.
How
That
does
is
it change? What in your reasoning? What changes?
this condition, the Dirichlet condition here.
But
You
it's-
have the new left, no?
Hmm?
If you have it in a circle, you.
Sorry,
left.
left or right, yeah, whatever. I mean, yeah, if the standard model is left, sorry.
Dirichlet condition is imposed on the left.
Yes, then this is left, this is right.
We should talk about this a little bit.
Yeah, where this left is the standard model. I mean, the same chirality as the standard model.
We can talk about
Yeah.
afterwards. I think.
So now let me go to the experiments of the beta decay, tritium beta decay, such as KATRIN, which has a tritium source and measures the beta decay energy spectrum near the end point, which is about 18 keV. So essentially, if you take just without just a neutrino, which has some mass, then the spectrum of the beta decay is this one, where delta E is the difference of the energy from the endpoint, and should coincide. And it starts when the neutrino has a mass mu. So this mass is small compared to the is near the endpoint, and then you have this spectrum. So this is a typical way to determine the neutrino masses. However, if there is let's say, a sterile neutrino that mixes with active neutrino with this way, so you have this is the active neutrino, this is the sterile neutrino, then the sterile neutrino, let's say, will be heavier. So suppose that it's produced at this point. So if you add this curve to the previous curve, you find that the energy spectrum contains a kink at the position where the sterile neutrino is produced. So that's the main observation. That's the sensitivity. So the energy resolution is about 0.4 electron volt, and okay, that's the way they go down up to 40 electron volt. So now, using the previous results, we can identify two regions of the parameter space, which can be analyzed analytically. One region is the region where the bulk mass is small, and therefore is a small correction to the Kaluza-Klein spectrum. Okay, there are two parameters here, there is the mu and c, so there are two different, c is the bulk mass, so you can have zero bulk mass or non-zero bulk mass. And here the spectrum should have a series of kinks, and these kinks should correspond to the production of each Kaluza-Klein excitation of the right neutrino. So that is, I find this very interesting. I mean, it's the analog of accelerators when they produce a resonance. By studying this beta decay spectrum, you produce the Kaluza-Klein resonance, and you find a kink. So this kink corresponds to the resonance. Then you can continue to have a series of kinks. And that's the energy resolution, the present energy resolution, 0.5 micrometers. The other case is a case of the large bulk mass. So it's a case, for instance, that was discussed before. So the Kaluza-Klein states are on top of the mass gap of the bulk mass. But then you can find a region in the parameter space in which the differential beta decay, when you sum over the Kaluza-Klein states, it takes a form very similar to what is called 3+1. In other words, it behaves like a sterile neutrino, an extra sterile neutrino with an effective mass, which is the bulk mass of the neutrinos, and an effective angle, which is given by this ratio of the parameters.
You mean if you add the effects of all of them, that behaves like that?
Yes, it behaves like that. Yeah. In a particular region of the parameter space, which I will show you now. So that is the result of the 3+1 model of KATRIN. So this is let's say that's the mass of the sterile neutrino versus the mixing angle. So this analysis can be done. This formula that I said here can be applied only at this region here. Above the other region is this formula. This approximate formula is not correct. So if you translate now this exclusion plot to the plot in the two parameter space, which is C bar and mu bar. So both of them are dimensionless and in units of the compactification scale. One is the Yukawa coupling and the other is the bulk mass. Then you can translate it to an exclusion or a positive sensitivity plot for this two parameter space. One can also use oscillation data again to, I mean, this is for NOVA, this from this paper here. So again, it's the bulk mass relative to the Yukawa mass. And then you can explore a region of the parameter space. So that's what is excluded and what is allowed from this data. Now this beta decay experiments, they're going to continue. The KATRIN essentially stopped. It's upgraded to, the first upgraded is what is called Tristan, which however its focus is at the KV masses with this resolution. So the resolution is not much. What is more interesting is the Ptolemy, I find. So this is a proposal that has been approved. And this is going to scan the whole region of the spectrum, of the energy spectrum, with an energy resolution of 50 milli-electron volt. So within 5 years of data, they can explore completely this region. So that would be very interesting to, because with this energy resolution, you explore really. And I mean, it can apply to both. In other words, for them, you can, because I had discussed with some the people who participated in Ptolemy from Princeton University. They can choose, tell them which part of the region they can scan. They can scan it, let's say, 1 kV or 10 kV, and then they can scan it with bits of 50 milli-electron volt. Is again better tritium better decay.
And what's the time span for that?
They are building the detector, no? I mean, they essentially, yeah, it will be installed in Heidelberg together with KATRIN. Where is KATRIN?
Time scale is what? 1 year, 10 year, 5 year?
Can start within a couple of years.
I don't know, but I think that
This is what I was told.
yeah, well.
Okay, so I go to the conclusion. So one of the first messages that concerning the Swampland is that the distance conjecture is that there can be some there may be an indication that the smallness of some physical parameters is a signal that we live in a large distance corner in a string landscape. And such parameters can be the dark energy or the supersymmetry breaking I didn't talk about.
Sorry, it's crucial that it's not supersymmetry breaking. The scale that this gives you a dark distance. It's not. So there are two different effects in string theory. We can easily have scales like hierarchy or supersymmetry breaking will be zero without going to.
Of course, yeah.
So the smallness of those parameters. So I think.
I mean, it could be also.
I think it should be clear because that's precisely the difference between the usual large extra dimension scenario where they're trying to explain the electroweak hierarchy as leading to a large extra dimension. That's not what distance conjecture demands. Because those correspond to the cases where you have dynamical, strong dynamics, like in weak scale and so on, or QCD and so on, which is not exponentially small. Those will not demand infinite distance. Whereas
if it is due to an extra dimension, though, it's a similar effect.
No. I'm saying that having small, so the motivation for large extra dimension being.
Oh, yes, I agree.
Those scale of supersymmetry breaking or hierarchy being small is not, in string theory context, does not lead to large distances. It can be done in small distances. Whereas the dark energy is different. The dark energy being small, you need a large expansion or a string coupling going to zero. So there are two different effects. It's crucial that the motivation from the quantum gravity perspective is not having, let's say, Higgs wave to be small. Higgs wave can be small at finite distance in string moduli, as we know very well.
Yeah, but for instance, when you try to break supersymmetry at a scale which is less than the string scale, then you find again that there should be a tower of states that show up at a different scale, though, because it depends.
There are two different effects. One is quantum field theory effects. Those can be at finite distance, and then there's quantum gravity effects. Yeah. Those are the ones which are be at infinite distance, because we can get to strong coupling physics or tower of light states and so on in quantum gravity at finite distance, which is strongly coupled. That's a different story.
Yeah.
It could be like masses go to zero. You can have conformal field theory in the middle of moduli space at finite distance.
Yeah, you cannot exclude such, but even for
that will not demand large dimension. It's crucial that the large dimension is driven by quantum gravity effect, not quantum.
I mean, even for the cosmological constant, you cannot exclude the possibility that there is a vacuum in which there are cancellations and the cosmological constant is small without being
at the... that the demanding from quantum gravity, that large distance gives you a tower, correlates with quantum gravity. In other words, this having just the mass scale being small is not enough. It's more than that. It's not just any parameter being small demands.
Yeah, I agree. Yes, there should be some motivation. But maybe I take just parenthesis, I have some time, just to mention something that a question that was mentioned before, Suppose that you take the last dimension, you have the potential here is 1 over R to the 4. And you ask what happens to the brain if you break supersymmetry. I mean, the brain can be non-supersymmetric, but then if the coupling, to transmit the supersymmetry breaking from the brain to the bulk, you pay with a gravitational correction. So it will be M, let's say M SUSY, where this M SUSY is a breaking of supersymmetry on the breaking, divided by M Planck. And this gives again the same scale, the millimeter, the micron scale. So the question is, if you, for instance, that could be a possibility, in principle, an ingredient, how to cook up a model in which you can have this
You're trying to say that
setup.
we can predict the scale of supersymmetry breaking on the brain
Yes.
based on one of our
Yes.
what scale do you get? there?
TV.
What?
TV.
TV for one extra dimension, you get
Yes.
TV.
Yes.
How do you explain that?
I mean, from here.
Sorry, explain that. more.
If on the brain there is the supersymmetry breaking is a TV,
Yeah.
then the supersymmetry breaking from the brain into the bulk will be suppressed by the gravitational correction. So it will be M SUSY over M Planck.
Yeah.
I mean, the scale will be M SUSY square over
So
M
that's
Planck.
the 10 to the
And this is 1 over R. I mean, the same. It's milli-electron volt. I mean, that's TV is, yeah. So it's 10 to, let's say, 10 to the 3, 10 to the 4, minus 15.
TV or GV?
TV, or 10 TV, take the 3.
For example, then I also have like a contribution to the tension of the brain, which is M SUSY to the 4.
No, but that's the thing. On the brain, the supersymmetry is broken scale should be at the TV scale.
Yeah, but then I'm gonna get like a document is gonna have one brain of TV to the 4.
TV to the 4, but that's exactly the thing.
Yeah, but so that way you have to find in a way. On top of the ball.
With the additive, you mean?
Yeah.
I mean, in terms of the bulk of the 5-dimensional, the scale is 1 over R. So here I discussed the neutrino physics, which the conclusion is that if the right neutrino propagates in the bulk, independently if they have the bulk masses or not, if the bulk masses, of course, are not up to the KV region, the tritium beta decay neutrino mass experiments could probe that region within 5 years. So thank you.